Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 10.2 of your textbook, which introduces us to the idea of how to do calculus with parametric curves. In the previous video, we spent some time just understanding the definition of a parametric curve and just taking a basic look at how you would build graphs of parametric curves through the sort of most brute force method available, which is just making tables of values. In this video, we're going to continue to sort of look and understand how to graph parametric curves, but we're going to do that from a more advanced perspective by using some calculus-driven techniques. If you think back to your Calculus 1 class, or even sometimes in this class, understanding things about the derivative and the slope can be very, very useful when trying to draw the graph of a curve. So, our main goal in this sort of first part of section 10.2 is going to be to understand how to determine the derivative of a parametric curve and then use that to actually graph some more complicated parametric curves. So let's go ahead and take a look at this. So our setup here is we're going to suppose that we have a parametric curve. So x is x of t and y is y of t. So both x and y are functions of some other variable, the parameter t. And what we want to do is we want to figure out how can we determine the standard derivative. And what I mean by the standard derivative is the derivative of y with respect to x. In other words, as we move in x, what happens to y? That's our standard derivative. That's the derivative that you calculated all through like Calc 1. Anytime you calculated a derivative here, we've always been interested in how does y change as you move in x. Now, of course, that's a tricky question because we know that x and y are both based on this parameter t, yet the derivative we want to understand is how does y change as x changes. So let's explore how we would sort of examine this. Well, the main idea is we're going to think of y as a function of x and x as a function of t. Now, the setup in general for a parametric curve is that x is a function of t and y is a function of t. But since we want to try to determine this derivative, y, the derivative of y based on x, we're going to think of y as a function of x and x as a function of t. Now, of course, if y is a function of x and x is a function of t, y is also a function of t. Okay, so how does this help us? Well, then what we could do is we could say that dy dt, the derivative of y with respect to t. Well, if y is a function of x and x is a function of t, that sounds like chain rule. So we could say that dy dt is the derivative of y with respect to x. That would be the derivative of the outside, so dy dx, and then times the derivative of the inside, treating x as a function of t. So that would be dx dt. So in other words, the derivative of y with respect to t is equal to the derivative of y with respect to x times the derivative of x with respect to t. Now remember, our goal is to figure out the standard derivative, dy dx. So we can solve this. We can divide this over here, and we can rewrite, and we should be able to see that dy dx is equivalent to dy dt divided by dx dt. And there we go. We've established our result. So in other words, to figure out how y changes based on x, what we do is we do the ratio of how y changes based on t divided by how x changes based on t. So in other words, the derivative of y with respect to x is equal to the derivative of y with respect to t divided by the derivative of x with respect to t. In terms of how we're going to do this once we get into our examples, well, since we'll have a function x of t and y of t for both x and y, we'll just simply differentiate for the numerator the y of t function, and we'll differentiate for the denominator the x of t function. We'll take the division there, and that'll give us our standard derivative, but in terms of our parameter t. Okay, so let's quickly summarize this and also see how this can be extended to the second derivative. Now, most of the time, just understanding the first derivative is sufficient to build a graph, but sometimes concavity is useful when graphing, so we might as well also know how to do the second derivative. And it's very easy to get the second derivative once you have the first. So, in summary, if you have a parametric curve, x equals x of t, y equals y of t, then the standard derivative can be calculated as dy dx is dy dt over dx dt. That's the result we just derived. Now, we can extend that to the second order derivative. The way we do that is we let y equal dy dx. So if you let y equal dy dx and you differentiate that, well, that'll be your second derivative. So what you would get then is that the second derivative, so the second derivative of y with respect to x, is the derivative with respect to t of dy dx. So in other words, the derivative with respect to t of this expression over dx dt. So in other words, if you want to calculate the second derivative, first you need to determine the first derivative, then you differentiate that first derivative with respect to t, and then divide by another factor of dx dt. What's the explanation for that? Well, again, we sort of said in our standard formula, we're basically saying that the derivative of x, the derivative with respect to x of y equals, just writing this out a little bit differently, derivative with respect to t of y over the derivative with respect to t of x, right? That's just sort of writing out what we originally had here. So now let's go ahead and let y equal dy dx. So then you'd have the derivative with respect to x of dy dx would be the derivative with respect to t of dy dx divided by the derivative with respect to t of x. Now, just rewriting all those, instead of having this derivative with respect to the sort of more standard notation, that would be the second derivative of y with respect to x would be the derivative with respect to t of dy dx over dx dt. And you'll notice that that expression right there is exactly the one that's stated there. So now, based on this summary, you guys know how to calculate both the standard first derivative and the standard second derivative of a parametric curve. And again, when we say that you can calculate these standard derivatives, we mean you don't need to remove the parameter. You can leave everything in its parametric form, and both of these, this dy dx and this second derivative, will both be in terms of t. So they'll still be expressions based on the parameter t, but they're calculating the standard derivatives between y and x. All right, let's get into looking at some examples. So these examples will sort of have a twofold purpose. One is they'll just allow us to sort of practice these two formulas here, but they'll also show us how the derivative information can be useful when sketching a graph. So let's go ahead and take a look. So we're going to consider the parametric curve x of t is sine cubed of t, y of t is cosine cubed of t for 0 to t to 2 pi. So we have a little restriction for where we're going to be looking. We're going to do a bunch of things with this. We're going to determine an expression for the first derivative, for the second derivative. Then we're going to use the first derivative to figure out all locations that have a horizontal tangent and all locations that have a vertical tangent. And then we'll put all of that information together to sketch a graph of this parametric curve. And then, as always, we'll indicate the direction it's sketched as the parameter increases from 0 to 2 pi. Okay, so let's just rewrite real quick. We have x equals sine cubed of t and y equals cosine cubed t. So for a, if we want to do dy dx, we would say dy dx is dy dt divided by dx dt. So how do we determine dy dt? Well, we differentiate this with respect to t. So that would be a chain rule. We drop the 3 down, 3 cosine squared, then take the derivative of cosine, which would be negative sine of t. And then divided by our dx dt, well, same thing, chain rule, 3 sine squared t, and then derivative of sine, which would be cosine of t. Looks like we could do a little bit of simplification. We could cancel out these 3's. Looks like we could cancel out a single sine and a single cosine as well. So it looks like we would end up with negative cosine of t up top, and in the denominator, just sine of t. Now, could we rewrite this as negative cotangent of t? For sure, but I'm just going to leave it in its fractional form. So this gives us an expression that if we know the value of the parameter, if we know t, we can plug it in here and we get the standard derivative. In other words, the slope of the tangent line. We understand how y is changing based on how x is changing. All right, let's use this to get the second derivative. Usually, again, the first derivative is all that you need for graphing, but just because the second derivative is something you guys have seen in the past in like Calc 1, we should be able to get that as well. So if we want to get the second derivative here, well, According to our expression, what we'll need to do is do d dt of dy dx, so negative cosine t over sine of t. So notice our numerator is doing the derivative with respect to t of this dy dx, so this expression right there, and then divided by dx dt. All right, the derivative d dt of this, I guess since we left it in a quotient form, we'd have to use quotient rule. So we take the derivative of the top, that's going to be sine of t times the bottom. Should also close that up. Looks like we'd get sine squared, and then minus, we leave this alone, differentiate this, you're going to get cosine of t, so we'll get plus cosine squared of t, divided by the denominator, squared, which is sine of t squared. Then down here, dx dt, we could recalculate it, but remember dx dt was right here, so we can just use that. And we get 3 sine squared t cosine t. Now we can do a little simplifying. This denominator can swing down here. The denominator of the numerator is really in the denominator. So we can swing this down here. And of course, this just becomes 1. So it looks like we get 1 over 3 sine to the 4th t cosine t. So again, this gives us an expression that if you know the value of the parameter, if you know where you are in terms of the parameter, you can plug it in here and get an expression or get a value for the second derivative. In other words, the concavity of our curve. All right, let's go ahead and now use part A specifically to locate all the places that have horizontal tangents. So for C, we want to know horizontal tangents. What are horizontal tangents? That means moments where our curve has a tangent that is horizontal. In other words, those are moments where something like this happens, or something like this happens, or something like this happens. In other words, they're important moments to know about. What causes a horizontal tangent? Well, a horizontal tangent is when the slope is 0. So these are moments when dy dx is equal to 0. Well, if we have this expression for dy dx, how is a fraction equal to 0? Well, the numerator would have to be equal to 0. So we'd have negative cosine t over sine of t equals 0, which would imply negative cosine of t equals 0, which would imply that this occurs at t equals pi over 2 and 3 pi over 2. It would, of course, also occur at like 5 pi over 2 or 7 pi over 2 or all those multiples. But remember, we're working exclusively on 0 to 2 pi, so don't need to worry about those. So, in other words, we will have horizontal tangents at these moments of the parameter. Now, are these the actual points where those horizontal tangents occur? No, these are just the values of the parameter. When we go to sketch the curve, we'll want to make sure to plug these in and actually get the coordinate, the xy coordinates of those points. For now, though, let's go ahead and do the vertical tangents. Vertical tangents are moments where your curve has a vertical tangent like that. So these are moments like this. That would be a vertical tangent, or something like that. That would be a vertical tangent there. So vertical tangents also important for understanding the graph of something. They're sharp corners, in other words. So if we go ahead and think about that, that's where dy dx is undefined. So horizontal tangents are where the derivative is 0. Vertical tangents are where the derivative is undefined. Well, how would our dy dx expression be undefined? It would be if that denominator was 0. So this would be sine of t equals 0. And of course, that would immediately give us values like 0, pi, and 2 pi. So we now know some locations where it has horizontal tangents, and we know some locations where it has vertical tangents. We also know a little bit more. We also know that at any point or any value of the parameter that doesn't match these, then it doesn't have horizontal or vertical tangents. So there are no other places where it can have sharp corners or go flat for a moment. So remember, this is not only telling you the locations of important things, but it's also telling you that there are no other important locations, right? So you got to remember, it tells you really 2 pieces of information there. All right, now let's go ahead, give ourselves another page and actually graph this thing. So for E, we still would like to go ahead and make a table of values, still need to know some points here. So we'll have our t, our x, I believe, was sine cubed. So we have sine cubed of t for x. And for y, we have cosine cubed t. Now, certainly for t values, we should definitely make use of the ones that have important things happening at them, like horizontal or vertical tangents. So we'll definitely make sure to put in like 0, pi over 2, pi, 3 pi over 2, and 2 pi, because those were all important. We can also make a note that at things like 0 pi and 2 pi, these are moments where our curve has to sort of go vertical. So I'll make a note of those. And these are moments, at least instantaneously, where we have to have a horizontal tangent. And we should probably have a couple other values. We don't need to plug in too much more, but we could, of course, always plug in something like pi over 4. That's easy to evaluate. Maybe like 3 pi over 4, maybe like 5 pi over 4, or 7 pi over 4. Notice I'm just picking out some points that are in between these things, so we sort of know what's going on in between. So let's plug these in then. So if we plug in 0, looks like we should get 0 and 1. If we plug in pi over 2, looks like we should get 1 and 0. If we plug in pi, 0 and minus 1. 3 pi over 2, minus 1 and 0. 2 pi, we would get 0 and 1. If we plug in pi over 4, remember sine and cosine would both be root 2 over 2. So we're going to get root 2 over 2 cubed. 2 over 2 cubed. And this would also be root 2 over 2 cubed. For 3 pi over 4, sine is still going to be positive, but cosine will be negative. So we'll get root 2 over 2 cubed, negative root 2 over 2 cubed. For this one, they'll both be negative. So negative root 2 over 2 cubed, negative root 2 over 2 cubed. And then for this one, sine will still be negative, negative root 2 over 2 cubed, but this cosine will be positive. It might not hurt to go ahead and maybe get like a rough sort of approximation for those. So we could see if we can just like quickly get a sort of value for that. So square root of 2 over 2 is roughly about 0.7, and if you cube that, you should get something. These are sort of roughly about 0.34 or so. So we can say that these are all going to be about 0.34. It doesn't really matter as long as we sort of know that they're both positive or positive negative, negative negative, negative positive. We're just trying to get a rough graph here. Okay, so let's go ahead and draw on our axes. Since everything is limited to being between -1 and 1, we can sort of scale pretty small here. So we'll sort of give ourselves a little bit more accuracy. So we'll go by 1/2. Okay, so technically our first value of the parameter is at 0, which was the 0.01. So our first sort of starting value, 0, 1, is up here. Then the next one would actually be at that pi over 4, where it was 0.34, about 0.34. So it looks like it would be something, maybe right about there or so. And then that would be pi over 4. So the next one would be pi over 2, which would be 1, 0. So we'd get this point here. Now remember, we also have a little bit more information. We know that at that first one that we put down, this has a vertical tangent, and at pi over 2, it's supposed to have a horizontal. So let's just draw those on 2. We can just put a little vertical line there and a little horizontal line there. Okay, so that was pi over 2. Now we have 3 pi over 4. That would be the next value of the parameter. That would be positive 0.34 and negative 0.34. So it looks like we'd have something right about, sort of there. Then that was 3 pi over 4. So the next one would be pi, where we have 0, -1. And so then that would put us down here. And of course, it would be vertical there again. Then after pi, we'd be at 5 pi over 4, which would be negative 0.34 and negative 0.34 abouts. So something like right about there. Okay. Then after 3 pi or 5 pi over 4, we'd be at 3 pi over 2, which would give us the point -1, 0. So we'd be over here. And of course, it would go horizontal there for a moment. Then we'd have 7 pi over 4, which would give us negative 0.34 and about 0.34. So we'd be up here. And then finally, the last value of our parameter, 2 pi, would give us 0, 1. We'd be back to here, and it would be back to being vertical. So again, let's remind ourselves, this was 0, pi over 4, pi over 2, 3 pi over 4. This was pi, 5 pi over 4, 3 pi over 2. This was 7 pi over 4, and this was 2 pi. So we need to go from here to 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 here back to here. So it might be tempted, sort of like just connect these, but remember you got to go through this, and you also want to make sure that it's vertical here, comes through, connects here, and then goes horizontal there. Then backs back out, vertical there, comes through there, horizontal there, and goes through there, and vertical there. So if we were actually to fill that in, looks like it would look something like that. This guy would go like that. Something like that. And there we go. A little wobbly, but there we go. That's our graph there. This is actually a famous shape. This is called an asteroid. It's sort of similar to a circle, but actually the interesting thing here is that it has got the exact opposites of a circle in terms of the derivatives. If you think about a circle, the derivative here would be flat, then it would go vertical, then flat, then vertical, and then back around. This is the exact opposite. This is vertical here, then flat, then vertical, then flat, then back to vertical. So the asteroid is actually sort of an inverted circle here. So notice that this was easier to sort of graph because of the fact that we had that extra information of the tangent lines, right? When we were going to connect this, this, and this, you could maybe argue that the only way to connect them is like this, but now we know that this has to be vertical here, has to come in here, and has to go flat. You might say, well, how do we know that it doesn't come in and do something like that? Right? I mean, that would look really weird, but also notice that that would cause it to go vertical again, which we know it can't. Because remember, not only did we identify places where it does have a horizontal or vertical tangent line, we identified the only places. So that means there were no other moments where it could go flat or it could go vertical. So it had to be connected in this way. If we wanted to draw in the arrows that traced it out, remember we went from here to here to here, here, so on and so forth. We're going around in this sort of clockwise direction here, tracing it out like that. Okay, so that's our first example of drawing another parametric curve, but making use of the calculus to help us there. Did we really need the second derivative? Not really, but if we wanted to, notice we could look like right here. If we wanted to know like what happened at the second derivative right there, remember this was t equals pi over 4. If we go back to our derivative expression here, if we plug in pi over 4, then this right here would be root 2 over 2. This would be like root 2 over 2 to the fourth. The main thing though is it would be positive. So that would mean it has positive concavity. So if we also look at our derivative here, so at t equals pi over 4, this guy would be negative, this would be positive. So that means decreasing but concave up. Decreasing, concave up, that looks like this. Notice that that's exactly the type of piece that we drew. Something that is decreasing, got a negative derivative right here, but concave up because it has a positive second derivative. If we wanted to be really, really careful, we could have checked the first and second derivative at all these points to make sure it lined up. But of course, that's way overkill for drawing these. But just wanted to make sure that you guys remember, second derivative gives you concavity. All right, let's take a look at one more example of doing this here. So we've got another sort of parametric curve here. So we're going to look at the parametric curve x of t equals t cubed minus 4t, y of t equals t squared. Once again, we're going to be sort of on a restricted little interval here. We're going to work from -3 to 3. We're going to do the exact same sort of lineup. We're going to figure out expressions for the derivative and the second derivative, use them to find all locations with horizontal or vertical tangents, and then sketch a graph of this parametric curve and, again, indicate the direction that it's traced out as we increase the parameter. So let's go ahead and start with expressions for the first and second derivative. So we'll just make a note here. X is t cubed minus 4t, y is t squared. So if we want dy dx, we know that that's going to be dy dt over dx dt. So what's the derivative of y with respect to t? Well, it would be 2t up top, and then the derivative of x with respect to t looks like it's going to give us 3t squared minus 4. So there we go. There's our derivative of y with respect to x in terms of our parameter t. For our second derivative, right, what we're going to have to do there is we're going to take the derivative with respect to t of what we just found, 2t over 3t squared minus 4, and then we're going to divide by dx dt, so we'll have to have a dx dt down in the denominator. Okay, so let's go ahead and do that. To do this derivative, we would have to use quotient rule, so the derivative at the top is going to be 2 times 3t squared minus 4, minus, we'll leave the 2t alone, differentiate the bottom, which looks like 6t, and then we'll have 3t squared minus 4 squared, and then in the denominator, dx dt, we could recalculate it or just remember it's right there, so we'd get 3t squared minus 4. If we simplify this, this could swing down here, and it looks like what we would get is up top, we'd have 6t squared, but minus 12t squared, so that sounds like minus 6t squared, and then looks like minus 8, so that's our numerator, and then in the denominator we get 3t squared minus 4 cubed. So there we go. So there's our second derivative expression there. So once again, we've gotten expressions for both the first and second derivative of y with respect to x in terms of the parameter t. So if we know where we are in terms of the parameter t, we can understand the derivative and the concavity. All right, let's go ahead and find the horizontal tangents. So horizontal tangents, again, mean that dy dx is going to be 0. Since these dy dx's always come out as a fraction, right, the fraction's got to be, the numerator's got to be 0, so this means 2t equals 0, which implies that we're going to have a horizontal tangent at t equals 0. So when the parameter is 0, we will have a horizontal tangent. For vertical tangents, that means dy dx undefined. For dy dx to be undefined, we would have to have 3t squared minus 4 to be 0. I'll divide by 0, so 3t squared minus 4 equals 0. That sounds like we'd get t squared is 4/3, which would look like we'd get two sort of messy values, 2 divided by root 3 plus or minus. So it looks like we get 2 divided by root 3 as our values of where the derivative is going to be undefined there. Okay, so there we go. We've now found all the places where we have horizontal and vertical tangents. Remember, this also tells us that we won't have any other places that have horizontal or vertical tangents. All right, let's go ahead and give ourselves another sort of page, and we'll come up with our table of values for E. So we'll have our t values, and x was t cubed minus 4t, and y was t squared. So there we go. All right, we can just go, last time we sort of picked out the main ones. This time, why don't we just sort of go in order? So it looks like we should probably do like -3, -2. This right here, 2 over root 3. Root 3 is roughly about 1.7. So 2 divided by 1.7 is going to be just a little bit above 1. So the next one would be that -2 over root 3. Then -1, then 0, then 1, then 2 over root 3, 2, and 3. So I'm using all the integer values as well as those sort of two important moments there. Definitely, if you find any horizontal or vertical tangents, you definitely want to graph those on there. So remember, these are moments where it's going to go vertical, here and here, and this guy is going to be a moment where it goes horizontal there. Okay, so we've got all of that. Now let's go ahead and plug in and see what we get here. All right. So as we do this, let's go ahead and just plug in the -3 here. So that looks like it's going to be like -27 plus 12. So that's -15 there. And then, of course, this guy is going to give us 9. For -2, it looks like it's going to be -8 plus 8, so 0, and y will be 4 there. This -2 over root 3, like we said, that's going to be a little bit above 1. It's about 1.17, 1.2 or so. So if we use that and we go ahead and cube that, and then we minus by that, it looks like we should get like sort of roughly, again, this is very sort of just rough approximations, about -3. And if we pop that in the other one and square it, it should be about like 1.4. Again, I'm just doing very rough approximations to try to get just a general sense of this. -1, if we pop that in here, you should have -1 plus 4. So that sounds like 3 there. Oh, I feel like I messed up this calculation there. Sorry, we're just going to go back real quick. So yeah, so this should be about a little bit above +3, so about 3.1, excuse me, about 3.1 there. Then this -3 gives us a 3 there, and then -1 here gives us a 1. Then at 0, it looks like we should get 0, 0. At 1, it looks like we should be at -3 and 1. At 2 root 3, we're going to be about roughly negative 3.1, and then over here we'll be at roughly about 1.4. And then at 2, we'll be back at 0 and 4, and then at 3, looks like we'll get 27 minus 12, so about 15, and then 9 here. All right, so we've got our points. We'll go ahead and sort of do them in order as well. So we've got x values that range all the way from -3 to about 15. So I guess I'll have to, maybe I can use a scale of 3 for the x here. So I'll go 3, 6, 9, 12, 15, -3, -6, -9, -12, -15. So we're doing scale of 3. For y, it looks like the lowest we go is 0 and the highest is 9. So it looks like we just go like 2, 4, 6, 8, 10. So I guess a scale of 2. All right, our lowest t-value was -3, and that gave us -15 and 9. So that would give us -15 and 9 somewhere over here. Then we got at -2, we were at 0, 4. So 0 for x and 4, so somewhere like that. Then we got 3.1 and about 1.4, so maybe somewhere right about there. And again, remember, we're just trying to get a rough picture, but if we zoom in a little bit there, remember we can think about this as where it's going to go vertical. So far, it looks like it sort of comes through in here and then sort of goes vertical like that, right? Okay, so that was this guy right here. Now at -1, it's at 3, 1. So 3, 1 would be maybe right about there. Okay, makes sense again, because if we just think about it sort of piece by piece, if it's coming in like that, going in, okay, that would make sense that it goes vertical there. Then we also had at 0, it's at 0, 0. So it looks like we would hit here. And this is also where it goes flat. So it looks like it's going to sort of wrap in, come in here, and then go flat there. Okay, so that was our t equals 0. So now we're at -3, 1 is our next point. So -3, 1, somewhere right about there. Then our next one right here is at -3.1, 1.4. So maybe right about there. And again, it's going to go vertical there. And then We have 0, 4. Now this is sort of interesting. It actually goes back through this point, so it has a self-intersection. You guys haven't seen a lot of graphs that have self-intersections, but parametric it is possible. So that means that we sort of come through here, hit this thing, go vertical, go flat, go vertical again, and then come back through the same point. So even though it's distinct values of the parameter, the x, y coordinates are the same. And then we get 15, 9, so we get something sitting over here. So again, we go from here to here to here to here to here to here to here, back to here, and then out to here. So if we draw that in, it looks like it should be something that sort of comes through like this, goes vertical there, turns around, goes flat, vertical again, comes back, and then goes out to there. So if we try to carefully sort of draw that in, it comes swinging through here, hits there, bounces off there, and there we go. How is this actually traced out? Well, we came through this way, came through this little loop here like that, then through here, then through there, back up, and then back out that way. So this has a little sort of like inner loop like that right there. So there we go. So once again, pretty complicated graph. If you think about this, this is not a function of x because it doesn't pass vertical line test. And it's not a function of y because it doesn't pass horizontal line test. So it's not a function of x or y. It's a relation between x or y. Trying to undo the parameter here, remove the parameter, is very, very challenging. So this is something that has a nice, clean expression in terms of the parameterization. T cubed minus 4t and t squared are not tough expressions for a parametric, but it has a very sort of complicated graph here. And again, this hopefully demonstrates to you guys the power of keeping things in their parametric form. Notice it was also much easier, again, to graph this by the fact that we knew that this was the moment where it sort of turned around. This is the moment where it hit that flat point and then came back up. And then this again, because it's that vertical moment, is where it comes back around, sort of bouncing off that side there. So those horizontal and vertical tangents, absolutely essential for drawing parametric graphs. In our next video, we're going to finish up section 10.2 by looking at a few other calculus concepts that we can do with parametric. For example, we might be interested in figuring out the area inside of here, right? Areas are something we've studied extensively. We should be able to do that with parametric as well. We might also be interested in something like the length or the arc length, like how long does it actually take to go from here around this little loop and then come back to that intersection? Or how long is the overall curve all the way from here through that? Like if you followed that path, how far do you have to actually travel? So in our next video, we'll learn how to calculate areas and arc lengths of parametric curves.